No, yeah, of course. And thank you for having me. I'm going to share my screen. Thank you for that wonderful introduction as well. Today I am going to be talking about the code suite Eureka, which is an end-to-end pipeline for JWST time series observation. So this includes eclipse spectra and transmission spectroscopy. A little bit of just, showing the team. I do want to really make clear that basically this is a really large collaboration. I am only a small part of the incredible work that, a very small part of the incredible work that has gone into this code and this open source software. And I will talk a little bit more later on how people can get involved and contribute as well. So what will we cover on this talk? Just a little bit of an overview. We're just going to talk about Eureka. What is it? What is it used for? I'm just going to show a couple of literature examples. And then I'm going to talk about how to contribute in case people want to get involved, talk about just the basic functionalities of Eureka. A very loosely defined mini demo. Basically, we'll go over a small breakdown on how to set up Eureka on your laptop so that you can get started. And just a couple of conclusions on basically moving forward and thanking my collaborators and the people that came to see this talk. I will provide the slides at the end as well, but just there will be links throughout the slide that hopefully I basically wrote down without really like hiding them. So like you can see the full link, and hopefully that will also be helpful for people to look up resources after the talk or follow along as I give this talk. So Eureka, what is Eureka? It is, as I mentioned in the title slide, a JWST time series data reduction pipeline. And it is driven by an open source philosophy. And this is in order to encourage science-driven results as well as accessibility to research. Basically, the team wants to make sure that people who want to get involved in basically data science when it comes to exoplanet atmospheres can do so in the most seamless way possible. What is it used for? It's used to reduce JWST time series data. So it starts from the raw uncalibrated files, from the raw uncalibrated FITS files that you get from the MAST archive, and it extracts the exoplanet transmission and or emission spectra from these. So in literature, we can see basically Eureka being used already actively by and in the community. So I've listed a couple of papers here. I think the first one, or the one that made a really big wave, was the WASP 39B. I think this is a really good paper to check out just in general, because if you are trying to get started with Eureka and you want to understand a bit more, or maybe have a test case to play with, I really do think that people should check out the WASP 39B paper. It's a good place to start to try to recreate real data and recreate real results. So in terms of contributions, right, I talked about this being a big collaboration, basically compiled of the efforts of a lot of people, and that includes people in the community that want to contribute to Eureka. So if you do have a coding experience or software development experience, and you can think of ways to make Eureka better or add anything to it or suggestions to the code, there is a GitHub page that you can access. There's a little simple flowchart here on whether or how to contribute. The actual documentation for Eureka actually has a very detailed kind of contributing to Eureka section that goes over a little bit of the GitHub type of experience that you would need in order to actually contribute to the code. Highly recommend checking that out if you don't have GitHub experience, but feel interested on contributing or being a part of Eureka. So how do we do what we do, right? So like, how does the pipeline work? What are the basic functionalities or the basic things that it does in its most upper level? So Eureka breaks down the process of data reduction. So the process from going from these raw uncalibrated files to full planetary spectra into 6 stages. Stage 1 calibrates the raw data. So it converts what we call ramps to slopes for JWST observations. If a little bit of this jargon is new to you, don't worry, I will go over a little bit of the data structure and also provide resources in which you can go back and look at the JWST documentation to get a little bit better sense of what some of this jargon means. For stage 2, we do further data calibration. So this includes flat fielding, unit conversions that might be needed. And then stage 3 performs the background subtraction and the optimal spectral extraction. Stage 4 generates the light curves. So it bends the time series of 1D spectra along the wavelength axis and just gives you a bunch of light curves. Stage 5 fits the light curves with noise and astrophysical models using different optimization or sampling algorithms. And stage 6 uses all of stage 5 results to basically compile a planetary spectra and display it as output for stage 6. So again, going back to the first stage or the slide before this one, I included sort of pictures of the flowchart that is also available on the Eureka website. So if this looks small, make sure to go look at the documentation. But basically, you can see over here, we're starting from very raw stages of the data. And moving forward through the pipeline, we end up with planetary spectra, which we then use to analyze and characterize exoplanet atmospheres. A couple of intricacies. Stage 1 and stage 2 of Eureka are actually a wrapper for the JWST pipeline. So a lot of the information on how those 2 stages work is actually going to be found in the JWST documentation, not in the Eureka documentation. As I mentioned, these stages are mostly a wrapper of the JWST pipeline. So any doubts that you might have about how stage 1 or stage 2 works are better referred to the JWST pipeline documentation. Now, to better understand the actual intricacies of how Eureka performs the rest of these reductions in the stages that I just went over, so stage 3, stage 4, highly recommend checking out the documentation. And I will show over here that again, as I've mentioned, that the documentation itself is full of these flowcharts. It is a very useful resource. Highly recommend checking the documentation. The team has worked very hard on making this documentation accessible. So I really do recommend people checking it out. As I said, it does break down both the stage 3 and stage 4 data reduction stages of Eureka in a much more detailed way than I did for time's sake. So going back to the presentation, righty. So I also list here a couple of resources that I think are basically really important to kind of get you started with just even working with Eureka. So as I talked about the documentation, there's an installation part of the documentation that is also going to be helpful, especially with troubleshooting, a frequently asked questions section documentation that will also be useful for troubleshooting when installing the code. I gave the link for Mini Conda. This is just a small Conda installation. And the reason why we need this, I'll go over the installation of Eureka, but Eureka has a lot of dependencies that can clash with your own dependencies in your own local machine. So it's heavily recommended that you actually use a Conda environment to set up Eureka. And in this case, if you don't want to set up the full Anaconda, Mini Conda is a great resource to look at. The CRDS files, we will go over what that is, but they're basically reference files for calibrations from JWST, and those can be found here, just more information about them, but I will also show how to just set them up with the code automatically. The masked archive, so this is where you actually get all of your raw data. So if you're working, for example, with JWST data, you want to go to the masked archive to basically look for the data that you want. And we'll also go over a little bit of how that.
Oh, Giannina, I think we lost your audio for a second.
Oh,
Oh,
uh, can you hear me?
yes, I can hear you now. Yeah, we
Yeah,
lost it for just a second there.
my mic just turned off out of
Oh,
nowhere.
nice. Yeah,
My
I can hear you
headphones
good
just
now. They
turned off.
rejected this.
Yep. Thank you. So, and then moving forward, we also have DS9. So, as a late millennial, I really do love myself a graphic user interface. There are ways to basically play around and visualize data, but DS9 is usually my favorite and my go-to because it has a really good GUI that you can play around with. And you really get to visualize the data in real time without really needing to write a whole Python script to do it. Um, Highly recommend DS9. It's just good for quick visualization, especially when you're working in pipelines like this and trying to figure out where things might be going wrong or why things might be looking funky. It always helps to go back to the original data or the FITS files that are being outputted by Eureka along the way to look at what is actually happening. And DS9 is a really quick way to do it. So I included the link for that resource as well. Now, in terms of installation for the actual Eureka code, as we talked about, we want to set this up in a Conda environment. Heavily recommend. I have tried installing Eureka locally. I have not had the best luck. Obviously, everyone is welcome to try, but I would really recommend against it and just making a Conda environment. So basically here is just the breakdown of how you're going to install this, right? So you have a terminal, you create your Conda environment, and from then on, so for example, in this case, Eureka is just the name of the environment. So that can be whatever name you want to give your environment that you're working on. If you're working on a specific project, I usually name the environment after the project. Um, and then from there on, you're going to activate. So you want to make sure that you activate your environment because you want to be in there when you clone the newest version or like the most stable version of Eureka, which in this case right now is 0.10. And once you clone that into your environment, you can basically change directories into the Eureka directory and install all of the dependencies that you want or need. So in this case, for this command, we're just seeing JWST here. That's just because that is basically the most bare bone things that is recommended to install along with Eureka. But here on the right, encased in red, is a list of dependencies that you can add into this command. So the way that you would do it is that you would just basically put a comma next to JWST in this command and then add whatever other dependency you want and so forth. And basically this just lists a couple of dependencies that you can install alongside Eureka, which basically helps you run Eureka in different ways. So for example, you can install PyMC3 with this version of Eureka, which helps you basically use different samplers for the parameter fits later on in the pipeline. You can install Jupyter. It helps with convenience for people that really do like coding and working in Jupyter. So if that's something that you use, it's great to install it into your own environment. Now, again, this might work flawlessly for some people, but it always will depend on the software or the OS that people are working on, that they might have to do a little bit of different things. I really do recommend checking the documentation if this it basically these lines of codes don't work as expected, because there is some troubleshooting tips and guides. There are some computers that have processors that will need a little bit more massaging when installing Eureka, stuff like that. So again, this is heavily version dependent in terms of what version software you have installed in your computer. So truly, like, don't be afraid to check out the documentation for this, and don't get frustrated if this just doesn't work right away. You're not doing like necessarily anything wrong. I will kind of give an example. So right down here, oh, I have to move the Zoom controls. So right down here, I basically give a list, or just a very non-exhaustive, 2 commands that have been very helpful for me for troubleshooting when setting up environments. And basically, for example, and if you can see on my terminal, if I do which Python, and we're talking about just my local installation of Python, the one that I just used locally, it shows you where that is coming from, right? Let's say that you are in your environment and you do which Python, that should look different, right? So we can see here that in my computer, my local installation is under Anaconda 3 bin Python. In my environment, my virtual environment, basically the location for that Python is different. That, like, these are just small commands that can be really useful for troubleshooting. If you see, for example, that these 2 which Pythons look the same, that means that something is not necessarily right. All right, so cool. Moving forward. So for the pipeline, one thing that we do need to have are what I mentioned them earlier. They're called CRDS files. So these are reference files that the JWST pipeline uses for calibration for the data reduction part of their pipeline. So this just gives an overview. So you're going to want to find your bash profile file, or this file for ZSH users. And in that file, which is just your setup file for your terminal, basically you add these 2 lines. So what this basically tells your profile or your terminal is where to find these files that the JWST pipeline is going to need in the long run. And I provide some examples down here of how that path might look. So it's very personal as to where you want that those ancillary files installed. But you do need them to run the pipeline. So a little bit more into the data structure, right? And JWST data structure specifically, because this is, as we talked about, a lot of the examples that are available to the community with Eureka right now are JWST data, and highly recommend checking those out. So in order to understand a little bit of the type of data that we're working with, I did want to go over a little bit of the data structure. So I broke it down visually. I'm a very visual person, so hopefully this is helpful for the people, especially for people that have heard jargon like groups or integrations and don't actually know what that means. So JWST does what are called like non-destructive reads. So it reads what we call up the ramp, or the ramp is this yellow thing, which is our slope or our flux. It counts over time. And what this does is that the detector is exposed to light without really basically like without having a shutter. So it just reads in light. And of course, as time goes by, in our x-axis over here, as time goes by, light collects more and more and more. So that's why we see this this increase in light. There is a detector reset, obviously, not obviously, there is a detector reset to basically protect against saturation and all of these things. And you go up the ramp again. And this is just the structure of the data. And integration is just a set, a group, right, that finishes from the start of a detector reset to the end. So now that we have kind of an idea of the data structure, we can download JWST data from the MAST archive. People should have a lot, if the data is non-proprietary, everyone should have access to it on the archive. So I will show, because in this slide, I do break down some user tips on how to best search for data. Eureka also in its demo files, and I'll show it over here, has a way to show how to download Eureka JWST data using just Python. So you just run the script and it should download the data that you want. But if you're a little bit more hands-on and kind of like working with
Uh, Giannina, I think your microphone said no again.
Oh, there we go.
There we go. It's back.
My headphones hate me today.
That's okay. I think we just lost the last 30 seconds there.
Okay. So basically, if you're a little bit more hands-on and like just downloading the data directly from MAST, a couple of user tips that I give here. Searching for your observations by proposal ID is always helpful. So under select a collection, there's the option to search observations by proposal ID. You can enter, I entered a random WASP 39B proposal, but basically people can look up whatever proposal they want. Once you've kind of narrowed down your filters over here, so like, let's say you want to look at JWST data, specifically near spec data for this target. What filters you want, all of that. Once you've kind of narrowed down those filters, you can choose, in this case, I'm just going to choose one visit. You can choose your observations, add them to what's called the download basket. And this is a big thing. Usually the master archive by default has this checked. Make sure to uncheck it, because for Eureka, you will need what are called the raw uncalibrated files. So under here in this filter group, you want to have uncal basically checked. And you want to have science checked as well, just to make sure that you're not including any target acquisition data. And from then on, you should have all that you need. So again, just make sure to have this unchecked. It's usually defaulted by MAST that it will be checked, and that won't allow you to see the uncalibrated option here. You will see it as if there's no uncalibrated data, but it's usually because this is checked. And then from then on, you can download the data. So each of these folders contains one of the files that will be used by the pipeline. All righty, back to the slideshow. So one of the things that I want to reiterate is that Eureka itself, again, the team has done a lot of work in documentation and also providing demos for people and demo files for people. So I highly recommend not to kind of look over this resource. I showed it for a second when I was showing where the file is to run data download from using a Python script. But basically, it's in the GitHub repository. There's a folder called demos, and it is separated between JWST demos and HST demos, because Eureka also has the capability to work with HST data. So again, check those out, especially because if you're going to set up Eureka and you want to start working with it, one of the most important or core things of how Eureka as a pipeline works is what are called ECF files. And these are standardized files. ECF is short for Eureka control file. These are standardized files that the pipeline uses where the user states the important parameters for the pipeline to know how to do its job, basically. So it allows for direct control of the pipeline's behavior. And this demo folder on GitHub has template ECF files for basically all of the instruments that are set up to work with Eureka. So all of the instruments that Eureka is set up to be able to reduce data for, there will be a demo ECF file in the demos folder in the GitHub page. So again, highly recommend. You will need ECF files for every stage. So there is a template for there is a template ECF file for basically every stage of the pipeline. And I do want to go again, once you've downloaded all of your demo files, so once you've downloaded all of the template ECF files, renamed them, have a local folder where you want to work, and where you're putting all of the data to get analyzed. Basically, the next thing that you want to do is look at the actual ECF file. So this is Eureka is a very hands-on pipeline in terms of it's very important, especially for stages 3 and on, that the user is aware of target-specific things that might come in or become important when running the pipeline. Looking at the data visually. So this is where DS9 becomes useful, looking at the data visually, seeing if there's anything that stands out, anything that might need to be corrected, cosmic rays and stuff like that. These are things that will affect the data and will affect how the pipeline functions. So it's important in terms of, even though Eureka has been coded to be accessible and easy to use, that doesn't remove the fact that data reduction is a process that does require a hands-on approach. So it does require the user to be aware of how the pipeline works and how their data looks and works with respect to the pipeline. So having said that, I want to go over some quick and non-exhaustive, absolutely not exhaustive considerations for users at each step. So these are parameters in the ECF files that might actually make a really big difference on your outputs, or that might actually be really target dependent, stuff like that. So for stage 1, there is a group level background subtraction option. So this can be done column by column for most instruments, or row by row for NearCam. And this works well when the number of groups is small. So having this turned on is usually recommended if your number of groups is small. Jump detection. So the JWST pipeline does this thing where it tries to detect jumps on the ramp and by itself. And we have found, the community has found, that this specific part of the JWST pipeline might not work really well with time series observations. So it ends up flagging a lot of real data. So skip jump and jump rejection threshold are the two parameters in the stage 1 ECF file that control that. A couple of things that people do is either up the rejection threshold or simply turn off skip jump or turn on skip jump entirely. So they skip the jump detection part of stage 1. For stage 2, these parameters are usually tunable and usually tuned by people. So skip photometry. So this is true, or true when you want to keep, your units of your like base units. And the reason why you would want to have this basically turned on is that Eureka can just work right with this. So you don't really have to worry about unit conversion. And actually the uncertainties in the pipeline itself carry on a lot more accurately if you leave this state, or if you leave this stage of the pipeline as true. If you turn it off, if you turn it to false, This actually can help validate against stellar models and find contamination because it's in units that are easily readable to the human eye. So when you're looking at your plots, it might be a little bit easier to understand the outputs of stage 2 and the stellar spectra that is outputted. But again, usually if you're just going to go directly from stage 1 to stage 6, people usually leave this as true. Just because the uncertainties end up being not as scattered as when you turn it to false. For stage 3, so a lot of stage 3 works with doing outlier rejection and basically spectroscopic extraction. So there is in the ECF file, in the demo ECF file, it shows this, but there is a parameter that works with how what thresholds are basically used to do outlier rejection. So again, false is recommended usually for deep trances. True works well for shallow trances and eclipses. This is not necessarily a parameter that is available to all instruments. So if you don't see this parameter in one of your ECF files, it might be just because some instruments don't really use this parameter. It just depends on how the outlier rejection is done for that specific detector. And then again, this is also the stage where spectral extraction happens. So really being careful as a user about your aperture sizes. So your background aperture and your the aperture of your spectra or your data. And
Oh, I think we lost you again.
we're back.
We're back.
We're just gonna yeah, my headphones hate me, so we're gonna have to get to keep doing this dance.
That's
um
okay.
So for aperture sizes, again, this is very target dependent, very data dependent, and requires kind of user hands-on type of approach. Always helpful to look at for example, like an initial run and see whether the apertures look right once you have kind of an idea of what apertures work for what detector, but also just looking at your data. So again, this is where DS9 comes handy. This is where data visualization tools come in handy. And background subtraction per integration is performed at this level. So again, manually checking the output plots of stage 3 is always helpful because that's where you'll see, if something looks funky, if some data looks missing, if something was flagged incorrectly, if the aperture is just way off, you will be able to see this in the stage 3 output file. So always great to check your output files, especially in these later stages of the pipeline. Stage 4 focuses on the binning and outlier removal. So it has a couple of optional steps. One of them is sigma clipping. It also has the option to calculate limb darkening parameters utilizing exotic. And basically, this is done in stage 4 because if you're running the pipeline all the way through, basically, the stage 5 will use the limb darkening parameters that were outputted by stage 4. Basically automatically, as long as you set it up to do it that way in the parameter file, in the stage 5 parameter file. So you can have this turned on. You can also just have it turned on and provide your own limb darkening parameters, and that is done on stage 5. But I just wanted people to know that this is an option in stage 4 to turn this on and just calculate limb darkening parameters. And stage 4 outputs spectroscopic and broadband light curves. So again, another great place to look at your results from stage 4 and kind of see what might be going wrong. This is the stage where a lot of people who might have not worked with data before but know what, for example, transit spectroscopy is, might be familiar. with the output plots, because this is where you're actually seeing the transits and seeing basically what the transit of your planet looks like. So again, this is a great place to check output plots and kind of get a sense of whether things are working correctly or not. For stage 5, this stage works on light curve fitting. So it's very target specific, right? So for stage 5, there are two configuration files. There's the ECF that you're already familiar with. This will just tell the pipeline how to run stage 5, and there are useful parameters in there. Like don't neglect the ECF file. Go into the ECF file and look, play around with what's in there, but there is also another file for stage 5, which is the EPF file. It's a parameter file to specify planetary parameters. Usually I just remember it by like P parameter, so EPF. And this is a file that allows you to specify target specific planetary parameters for the fitting. It allows you to designate fitting methods that you're going to use for your planetary parameters and priors for these fits as well. Whether you want uniform priors, Gaussian priors, stuff like that is done in the EPF, whereas the ECF for stage 5 is still very technical in the sense that it's mostly how you run the pipeline, where EPF has a lot of target specific stuff that will be useful to specify for the fitting routine. And again, stage 5 does all of its magic, and stage 6 outputs the planetary spectra. So for stage 6, the ECF file basically allows for customization of output planetary spectra plots, and also allows for you to plot whatever model you want to plot alongside the data. So if you go into the ECF file, you will be able to kind of play around with some of the customization aspects of the plotting in Eureka, but also you will be able to input a custom model if you want to compare it against your data. For example, if you want Eureka to overplot the data over your model, for example. So that's very useful. Again, demos and the demos folder in GitHub is a very useful resource. This code is directly copy pasted from the demo file in the Eureka folder. This is basically the script that you use to run Eureka itself. So one of the things that I will say that is great about Eureka is that it is modular. So it is separated by stages because for a reason, right? And it is separated by stages for easy, like basically easy control of the pipeline. So what this means is that right here, I'm running all the stages, right? Just 1 through 6. Let's say that around stage 3, my pipeline breaks. So I run 1 through 6. Let's say along stage 3, my pipeline breaks and I'm not getting outputs. I'm not getting anything and I need to figure out what's wrong. I figure out what's wrong and I know what I want to do. I already have all of my outputs from stage 1 and stage 2, right? So you don't have to run the entire pipeline again. You can comment out these 2 lines and run it from 3 forward. So it is very modular in the sense that you can very much pick and choose what stages you're running along the way, granted that your ECF files are where they need to be, and granted that in the ECF files, you are specifying the right parent directory for all of the output files. So basically, one of the things that is really like great about Eureka, in my opinion, is this easy control of the pipeline. The fact that you can start and stop at any stage and play around, see how things are looking, see what things are happening. The reason why I think this is really useful to keep in mind is because, especially if you're running this in a local computer, so if you're a student that just is here to kind of learn how to set this up and how to get started with something like Eureka, and you're in your you're in your Mac laptop from like 2011, Eureka is going to take a long time to run. It depends again on the binning and it depends on a lot of user-defined parameters, but in general, The pipeline itself, if it's being run in a local machine, is going to take some time. So what I really like about how Eureka is set up is that if at any point anything breaks, you can start from where it broke or from where it stopped. You don't have to start from the beginning because again, it is a code that can take a long time to run. So you don't want to have to start all the way from the beginning. Um, Again, remember that once you have Eureka installed and you have the Conda environment activated, you can basically just run this file as you would any script. But this is, again, granted that you downloaded and edited your ECF files to fit the data that you're working with, or to actually like look at the data that you're working with, as well as downloading your own local version of this file, which is again found in the demos folder in GitHub. So again, as I said, this was kind of a very loosely termed mini demo in the sense that it wasn't really a live demo because again, I hope it's been clear by me going through the stages and how Eureka works that it is very data dependent and it is very dependent on the user and what they want to experiment with and play around with. So it can be really sandboxy in that way that it really does help to sit down with the ECF files yourself and try to figure out what things are going to make your data look better or have better uncertainty, stuff like that. In the interest of time, I didn't really do a live demo, but hopefully the resources that I've listed and the things that I did go over, the quick things, just like how to download data from MAST, what troubleshooting like commands on the terminal I can use to check that just even my Conda environment is set up correctly. I hope those are useful, especially for people that are interested in getting involved in this sort of research, but have necessarily have no background information or background knowledge on how data reduction, especially for time series observations, transit spectroscopy, and all of that works. So hopefully this has been helpful for people. And again, I really want to reiterate the fact that resources are
Almost made it to the end.
there we go again. All right.
There you go.
This will be the last time. um, so yeah, so hopefully this has been helpful and hopefully people kind of have a list of resources just from looking at this presentation, where if this presentation wasn't able to answer something that you have about the pipeline, some question that you have about the pipeline, you at least know where to look for the answer and you at least know who to contact for the answer. So for example, in this case, if people like see this talk and have any questions, I'm putting my email here. I'm very happy to basically respond to any more in-depth questions that people might have once they start running the pipeline, if they run into any problems. But I really do want to reiterate that Eureka has a ton of resources for this. The GitHub page is very, very useful for this. If you go into the issues in the GitHub page itself. So issues over here, we can see that people think like in the community have opened issues of problems that they've found when running the pipeline or trying to get the pipeline to work on their side. So in my opinion, this is the best place to go if you have a very technical question about whether the code is not working for you. So if the code technically in your machine isn't working right or working as it should in a technical sense, I would highly recommend going into issues and opening an issue on GitHub. If the problem that you're having with the pipeline is that you don't really understand your outputs or there's something that looks funky, I'm happy to try and help take a look at it. And hopefully, again, going back to these examples people check if you want to play around with data and test data, real data that has been used in literature. Again, highly recommend checking out this paper and trying to basically reproduce the results from this paper is a really good kind of place to start and try to get started with Eureka. Having said that, I also want to say this link is explicitly typed up here, and it is a link to these very slides. So if people want to be able to access some of these resources and don't want to like just look through the YouTube presentation to try to figure out what resource is and just want to look at the slides and copy and paste the link, hopefully this helps with that. And yeah, again, I highly recommend checking out the Eureka JOS publication for a little bit more about the philosophy of Eureka and why the code was basically why the collaboration works on this code and tries to make it open source and accessible to all. Highly recommend reading the paper for that. Yeah, and that's mostly all that I have. Hopefully some of this has been helpful for people, especially those that were looking to kind of just get started with Eureka or understand what Eureka is about and what it does. Hopefully this has been helpful.
This has been great, Giannina. This is awesome. Thank you so much for going through everything. I've like been taking some notes, but I'm excited to just like watch back through this presentation and actually have some data going at the same time. So thank you so much for talking to us about Eureka today. So we do have some time for questions. I have a few listed here, but if anyone has any questions, feel free to raise your hand or post them in chat, and I can read them off. But I'll kick us off. So just kind of going back to probably like the first couple of stages of Eureka.
Yeah.
You know, JWST has been around for, oh my God, like, is it 2 years now? But it's getting, the time is going fast, but it's still, you know, a very new instrument, and we're still learning a lot about how it calibrates and, you know, those sorts of details. So how does Eureka kind of stay up to date with all the quirks that we learn about JWST and other instruments down the line?
No, yeah, I think that is a great question. I don't know if I have a more technical answer than just basically if JWST is updated, usually the development team looks into tests. So it tests whether Eureka still works, and it basically just recommends people to update to the newest version of the JWST pipeline. Basically, again, it's a very top level wrapper that happens in Eureka for the JWST pipeline. So I don't know if there's a more technical answer than that. Again, there's amazing people in the Eureka team that might have a little bit more of a technical answer to this question.
No, that's great. So there's kind of like a lot of back and forth with, you know, when we learn more about JWST, the Eureka team has to kind of keep an eye on that. Yeah.
Yeah, and I think this is why it's important to reiterate how much of a community effort this is, right? I think that it's important that if people want to get involved, that they get involved, because I think open source software is just really important in general, and it does require time and effort from people and a lot of these sorts of back and forth. So the more people that are hands-on testing our code, working with our code, playing around with the code, it actually helps the team a lot to kind of discover pitfalls in the code and how to make it better.
Yeah, actually, that's like a really great segue into my next question, which is just kind of stepping back from Eureka and just looking at this project as a whole. What are things that you've learned in this process that you think others could take away when you're managing such a big project that has, you know, such a large collaboration? Like, is there any tips or tricks with open source science like this or pitfalls that you've encountered?
No, yeah, so that's a great question. I think one of my always cautionary tales of having worked on big collaborations for open source software. So I worked not only for Eureka, but also for AstroPi, AstroQuery for a bit. And I think that one of the biggest takeaways that I've had from this sort of collaboration is how important testing is. So how important it is to write comprehensive tests for whatever software you're working on. And not only comprehensive tests that users can run, but that the team actively upholds and runs as they make updates to the code.
Mhm.
Because with big projects like a pipeline like Eureka, a small change can actually break something along the way. And if you're not testing continuously, if you're not being aware of running the code after you make those changes, things can start getting really messy really quickly.
Right.
So I think one of the biggest takeaways of working on like big open source collaborations is for me that how important testing the codes are and writing comprehensive tests for your software. So a lot of people use PyTest and stuff like that. And these are just quick tests that allow you to see that the code's just working, and that whatever small change that you did or your colleague did is not breaking everything else along the way. So yeah, I think that is one of my biggest takeaways.
Yeah, no, I definitely have run into that. I tell early career scientists that the best scientists probably spend only like 3% of their time doing science, and 65% of their time writing documentation and tests.
Yep.
So,
Yeah.
um, yeah, just a quick one I was curious about. So you focus a lot on JWST, but does Eureka work with Hubble data or any other
Yes.
instruments? Yeah,
Yeah,
awesome.
so for Eureka also has the capability of managing HST data, and I know colleagues that are actively working on having it manage HST spatially scanned data, which is really exciting. But yeah, I focus mostly on JWST because the test cases that are out there, or the literature that is out there when it comes to papers that have actually used Eureka, put it to practice in science analysis and everything, have mostly been JWST data. But
Right.
Eureka is pretty much available to use for HST data as well. So with C3 data specifically.
Awesome. Very cool. All right. Does anyone else have any questions? All right. Not seeing any, but thank you so much again. This was a really, really awesome talk, and really excited to actually get in and try Eureka out in the future. But yeah, thank you everyone for coming out today, and let's thank our speaker again for an amazing seminar.